I'm very glad to be here. And so the idea of today is to present you some research direction of our group about causal modeling. So it is, as I said just before, it is not a formal presentation. So feel free to ask any question you have, and would be very happy to discuss about any subject you could be interested in. I would be very glad. So the idea of causal modeling, it is to strengthen research direction in trustworthy AI, and it is a concern for many of us. And just to teaser, it is this judgment of European Court. In fact, the need of trustworthy AI comes into play even in the law, and we have this recent judgment of the European Court asking for more interpretability in algorithmic decision. Here it was in Vienna, a decision about credit application for an iPhone. So it is just to tell you that we are all concerned with trustworthy AI, and it is a concern for everyone in European country. And so the idea is, what do we ask for a decent, trustworthy AI? So we may ask different things. So first, we want that any AI algorithm is fair, that there is no bias. We want also to be able to control uncertainty, to have reliable and accurate models. And we shall also discuss about what could be a good explanation, how can we provide a transparent decision, and how robust will be these explanations with respect to perturbation. And the focus of this talk is just to provide some answers that are provided by causal modeling. That could be an approach to answer these questions. So I will begin with something which is what is a causal graph? What is the aim of causality? So here you see that maybe you have some, I don't know, some causal graph, some relationship between income, physical activity, occupation, and so on. And many phenomena, socioeconomic phenomena or other phenomena, may be explained by a causal graph. So it is the causal graph. It is something which is quite easy in some sense to explain complex phenomena and to take into account the possible relationship between different factors explaining something, like, for example, physical activity. And using causality, in fact, we shall be able to answer several questions. So with classical machine learning, what we try to do, we try to predict, and it is mainly based on investigating purely statistical association. And with causality, we try to go a step further. So, for example, we want to estimate what we call a causal effect. For example, to see the effect of what could be the effect of potential intervention. So, for example, if I do some exercise, maybe it will have some effect of my cholesterol rates. And if we know the relationship between the different variables, maybe we are able to see what will happen if we intervene, if we decide at some point to, for example, to do more exercise, or to eat less chocolate, or to do something, okay, in an interventional manner, and what we will be the effect, for example, on my cholesterol rate, on my weight, on any target of interest. So the first benefit of causal approaches will be the estimation of what we call causal effect. The second benefit, the second goal of causal analysis is to investigate what we call counterfactuals. So, for example, counterfactuals, we try, for example, to imagine. So, imagine that I am applying to a job. I sent my CV, and I wonder what would have happened if I have been a man, what would have happened if I would have been younger, what would have happened if I have done one engineering school. So in fact, I try to imagine what would have happened if I changed something in my past, in my CV, in my experience, in my gender. I try to see what is the impact of possible change in my identity on a given target. So, for example, on my income, on the outcome of a credit application, of an outcome of a job application, and I try to see to explore all this possibility using what is called counterfactuals. And what is common to all this to these two causal questions is that we can do this if we have some information beyond the simple observation of data. If I have some causal hypothesis, if I know something which is called the causal graph, if I know that, I can do beyond the mere prediction, and I can investigate these two kinds of questions, investigate causal effect, investigate counterfactuals. And the point is that in many situations, maybe we do not know the graph, and we have also to estimate it. So we have also associated question, which is the estimation of the graph, and thereafter, how can we use this graph to go beyond mere prediction, mere vanilla machine learning questions. So it is what we claim is that considering causal modeling, we have some benefits. We can investigate and go beyond vanilla machine learning and investigate what we call causal questions. So just to show you some what could be the challenges in causal modeling, I just show you an example, for example, about medicine. So here you want to investigate, you want to understand what is the clinical response of some patients to a given treatment. And the point is that if you want to investigate this question in itself is a very complex question. Because when you consider the different patients, some people have some comorbidities. Some people have also some clinical history, which is this kind of data, the family history, if they have some surgery or not, previous treatments. For example, in the case of tumors, you may have metastases. So, in fact, if you just look at this question, which looks at first glance quite simple, in fact, it is a very complex question, and for several reasons. First, you have a different complex relationship between the factors. In fact, you have group of factors, and you have also a large number of factors. Here you have 60 factors. So in fact, if we want to summarize the different challenges, the first challenge is that we have a large number of factors, that we have group of variables, and also that we have complex relationships. and the fact, the research direction that we want to tackle in our group, if we want to summarize them, it is this 3 directions. How can we deal with large graph? How can we deal with group of variables? And how can we take into account, for example, uncertainty? For example, maybe we have some missing value, we have no knowledge about the relationship between these 2 variables. We have, in fact, some uncertainty in this graph. And what we want also, we want to be robust to any misspecification. So just to summarize, here we have the question of large-scale causal discovery. We have the question of causal inference with cluster of variables, and we have this question of uncertainty and causality. So today I will more focus on this question of cluster of variables. Okay, and if you have some question, we can also discuss about this large-scale causal discovery setting and this question of uncertainty and causality. We can also discuss on that, but at first I will discuss on this causal inference question. So do you have any question on this stage? Is it okay for everyone?
And feel free also to put your question on the chat. I can report them if you wish.
Yeah, if you have any questions, so feel free to ask them.
Excellent, thank you.
You have. Okay, so okay. Okay, so I will just focus on that. So just to summarize, in fact, we have several questions. We have a causal and non-causal question. We have this question of causal discovery. We have this question of causal effect, and we have this question of counterfactors. So to summarize all that, we have this ladder of Jude-Apple, which is a phasor of causality. Here, most of the time, you have vanilla machine learning based on observation and association. It is vanilla machine learning. We shall discuss a lot about this question of intervention. And also, if you have some question about counterfactuals, there is a lot of explainability techniques that are based on counterfactuals. Notably, probably you have heard about counterfactual explanation. I won't discuss that, but I would be very glad to discuss it with you if you have some questions. Okay, so just to discuss about you, I will just introduce a small vocabulary to explain you what are the way we encode, what are the main concepts involved in causality. So the main concept, it is the concept of the graph, basically. Probably you have heard also about Bayesian networks, which is another name for Markov factorization. And in fact, there is also this question of structural causal model. So I will give you some example of structural causal model. It is when you have a knowledge about the relationship you have between your variables. So it is not the case, for example, when you have, in the example in medicine that I just show you, it is not the case. But for example, if you have some physical experiments, in some cases, you have a true knowledge of your relationship between your variables. So for example, I advertise a very nice paper that I can mention, which is the paper of causal chamber. And in this case, they study some physical phenomena. And in this case, you have a true knowledge about the relationship you have between your data. Okay, so just to show you, it is just to summarize the different tools that are involved in causality. And I will begin with the causal graph. Thereafter, I will explain what are everything in the toolbox. So just to show you, to explain you what we have at our disposal, we have several variables of interest. Okay, so imagine that you have the age. The age has some influence, I don't know, maybe on the curriculum. It has also some influence on the income. And here, the curriculum has an influence on the diploma you have, and the diploma has also an influence on the income. So maybe you have some relationship, you have some basic knowledge about your graph. That is the relationship you have between your variables of interest. And then maybe if you are in a physical, you study a physical phenomena, you have some knowledge, you know maybe the relationship you have between x1 and x3, you know the relationship you have between x4, x2, and x3. So it may happen, for example, if you study physical phenomena, you have physical laws, or maybe if you have PDs, or if you have ODs, you have some knowledge about the relationship you have between your variables. And depending on the information you have, the point is that if you have a graph, you have basically you have a Bayesian network, and if you want to study the joint distribution of these four variables, you can have a factorization, which is called the Markov factorization. So the main tool of causality, it is these two tools. In fact, we have data, okay, that are, for example, data related to these four variables, but we have more information in terms of modeling. We have an information about the relationship between these variables, which implies something which is called the Markov factorization, which is a way to rewrite this joint distribution. And maybe in some cases, you have some statistical model. So imagine that you have a statistical model with some link function, and maybe you have that, and you have more information, and you can explain what are the link between your variables. Okay, so I will explain you now two tools which are very basic in the setting of causality. So I just will check that I have also these things. So just to show you why it could be something which is very natural. So we are going to talk about intervention. So just to show you, there is a very nice example, which is some data set from the European Spatialization Source. So in fact, what you have some liquid helium, and this liquid helium is, the idea is to cool some turbine, and you have a circuit of your liquid helium, okay? And then you have some natural link between your different checkpoints in some sense. So you have your liquid helium which is circulating. And the point is that, for example, maybe you want you detect an anomaly. And if you are an operator in this European Spatialization Source, maybe you want to intervene. And to intervene, it is something which is really natural in physics. To intervene, it is because maybe you see that the temperature is too high, and what you want to do, you want to set the temperature, or you want to have a lower temperature. So instead of I don't know 20 degrees, you set the temperature here to I don't know minus 50 degrees. So you set something, you do what is called an intervention, and since you have some effects, this temperature has an influence on this one, and this one, and so on and so forth. You want to be able to see the effect of an intervention. And to do so, we need some formalization of what is an intervention, and it is what I am going to explain now. So here, just to explain what is an intervention in a formal way. So imagine that you have some relationship between three variables, which are x, t, and y. If you want to intervene on t, it is something very silly. You intervene on t. That is, you replace this by a given value, and you replace these two relationships with 1. T is set to a given value, and then you have y. So it is intervention. It is something in the formal way very silly. And if you see, okay, it is something very in any physical phenomena, it is something which is in any industrial context to set a value, to intervene on an industrial phenomena. It is something so easy and so current that you will always do that. So you want to know, as soon as you have this notion of intervention, you just want to be able to use it and to see what is the effect of intervention. Okay. Is this notion of intervention clear? Is this do you have some question on that? Okay.
I
So
see a comment, Marianne, sorry, I see a comment from Freak. I don't know Freak.
Yeah.
Oh, sorry, Manuela, please go ahead.
I had one question, but it's answered by Wikipedia already. Thank you.
Okay. Please feel free to interrupt me. I will be very glad. Okay, perfect.
Yeah. So now we have Manuela, and then
that's maybe some provocative question. So there might be some things that you don't want to try, right? So I just want to ask: is there any mechanism to? I mean, like we could do simulations, but also there could be like
it's a point. You are fully true. In fact, intervention in the physical world, it is perfectly possible. But here, if you have, for example, a huge factory, or if you have, for example, a nuclear plant, you don't want to intervene physically. And what you want to do, you are perfectly right, and that's very nice that you emphasize this point. You want to be able to do this using only simulation, numerical simulation, that is a surrogate model. And you want to avoid any physical intervention. You want to use only simulation to simulate what happens if we are doing some physical intervention. And you are fully right. It is the core of the question. It is in all generality, it is possible to perform intervention in the physical world, but we want to avoid it, in fact. And it is really the point.
Thank you, Marianne. There is a question also from Christophe Guettier from Safran. Christophe, please.
Yes, nice to meet you and to attend your talk. So I'm deeply involved in the ICAPS community, which is a planning and scheduling community. And of course, in this community, we have been studying formalisms for causality for a long time. I mean, in planning, we used to deal with strips formalism, then with graph plan, or with PDDL, hierarchical task networks, and we've also studied all what is about task networks, like conjunctive task network or disjunctive task network, with or without uncertainty. So I was wondering how your work is positioning with respect to all the work's been done in this community, and with a lot of applications. Indeed, we can highlight a lot of application in aeronautic space, mainly defense. So.
Yeah. As far as I understand what you are mentioning with planning, I wonder if it is not something that we call sequence of intervention. That, for example, we may perform one intervention and one other one, just to have, for example, to target a given value for an outcome. If it is such
No. In fact, we have explicit causal representations, what we call fluents, for example.
Okay.
And it's all based in logic. So in general, it's a logical representation. We use different types of logical paradigms to solve the problems, like temporal logic, or we could use constraint programming, constraint propagation too. And it's been here for a long time. I mean, and we have a lot of results, of course, on completeness results, approximation results, and so on, because most of the problems are NP. non-deterministic polynomial. We have studied the border between NP-complete and NP-hard problems, and when you become NP-hard, all this. So there are many results you could use.
Okay, so maybe what you mean is that you have structural causal models that are made of logic, that are involving logic operation. It is what you mean?
Logical operators.
Logical
operators,
yes.
That's an approach, but you can have a language, complete language, like PDDL, that allow you to express a causality between action, because any action is represented as preconditions and effects. And of course, preconditions and effects can bind different actions. What we call a plan, in fact. The set of states you need to achieve a given goal, that's basically a planning problem. And there are multiple assumptions you can use to define a planning problem, and multiple ways to solve them as well.
Thank you.
And it's all about causality.
There is a little comment from Catherine. I don't know if, Catherine, you wish to mention. Said it's not same type of causality. Maybe it is just a comment.
Hello? Okay, hello. Yes, it is just to... Can you hear me, please?
Catherine said...
Hello? Yes, I was saying that... Yeah. Can you hear me, please?
Yes.
Yes. So the idea is that, in fact, there are some works of Gégère who wants to provide some more interpretability in, for example, in causal modeling using logical operators. So there are some works in these directions, and I have some colleagues at Grenoble who are working to want to promote interpretability, for example, of LLMs using logical operator. So it is something that the community is investigating. So in our case, we are more focused on classical structural causal model. And the reason is that we are working with physicists, and in our applications, the physicists are using, for example, ODEs or PDEs, and when discretizing their ODEs or PDEs, they have a natural expression in terms of structural causal model. But I think the direction that you mentioned is very promising, but it depends maybe on the application that you are targeting, maybe.
Thank you very much, Marianne. There is a question from Martin Gonzalez. Yes, Martin? I think I will defer my question for the discussion. It's about more broadly the fact what you can do when you can never observe the counterfactuals, but it's for later, I think.
Yes. What application do you have in mind, in fact?
Well, essentially, you can simultaneously run a machine at 100 degrees and 120 degrees and see the exact difference, say, in wear and tear at that exact moment. You can only see for the same machine one after the other, right? But I think this is a very general thing about counterfactuals that might be better to leave it for the discussion.
Okay, with pleasure, yes. So maybe it is the right time to explain what is the counterfactual. So the counterfactual, if we have a structural causal model, I will just explain it on an example, and thereafter, if you have some question about it, we can discuss it. That's a very good point. In fact, counterfactual, the starting point is an observation. So we have an observation, and if you remember, when we have a structural causal model, there are the variables that are observed, plus some terms which reflect the uncertainty that we have in our model. It is a noise, basically. So if we have an observation, we can calculate, in some cases, the value of the noise, or at least we can maybe estimate the probability distribution of this noise. And thereafter, having this distribution or this value of the noise fixed, we can intervene to see what would have happened if, for example, T has been set to another value, which is T new, and it is what we call counterfactual. So, in fact, as you mentioned, we need to know the structural causal model to perform intervention. Under some assumption, for example, of additive noise model, maybe we can estimate in some case this statistical model. But we need to set some assumptions about, for example, the way the noise is involved in the whole pipeline, for example. So, in fact, the counterfactual is a really difficult question. And what I want to emphasize is that for a given graph, we may have a lot of structural causal model corresponding to this graph. And then the notion of counterfactual, as you said it, is a very difficult notion. And it depends on the structural models that you have. So now I want to summarize and to summarize the questions that we investigate. Okay. So our starting point is data, as usual. We assume that maybe we know the graph, maybe we wonder how we can estimate it, okay? And some causal quantities is when we have a range, we want to compare the effect of an intervention with respect to another one. And there are several questions. How can we estimate the causal effect? And how can we also estimate the graph? So, Sam, if you have some question, please ask. And the reason is that, so just to recap the challenge that we have, the challenge it is we may have a large-scale learning of the graph. We may have cluster variables, and we may have also uncertainty to deal with. Okay. So what I propose is I give you just some insight each time of the way we tackle each challenge, and we discuss about it. Okay. So I don't know if you are all aware about causal discovery. So causal discovery in some case, for example, in the example at the very beginning that I gave you, in the example of the European spatialization source, we know the graph, but there are many cases where the graph is completely unknown, and there are several approaches to estimate this graph. So I will just focus on one way to do so, which is to use, for example, what is called the Markov blanket. And what I want to emphasize is that each time there are two approaches, so two main approaches. So the first approach is to detect some patterns, some local patterns in the graph, and to run several tests of independence. And if you see that there are several challenges, there is a choice of the test. There is the fact that we have a lot of tests to perform, so we have a multiple testing problem. And we have also, after that, to gather all these constraints to see the global structure of the graph. And the second method, it is what is called the noise-based method. It is when we try to learn a statistical model, for example, an additive noise model. In fact, there is only one correct way to learn this statistical model, and it is because there is some asymmetry, causal asymmetry in the model, and there is learning a statistical model can help also to learn the causal direction. Okay. Okay. Any question on that?
I do not see in the chat, just
Okay, okay,
yeah.
if there is no question, I will just, yeah?
Thank you. No comments now about the topic.
Okay, so causal discovery, in fact, there is a challenge, which is in the literature, we see that mainly causal discovery method tackles the problem of a few numbers of nodes. And what we want to do causal discovery in the large scale setting. So there is an approach developed by partners of Paris-Saclay, which is an approach based on divide and conquer, and the idea is in fact dividing in three phases. So at first, what we do in phase one, we identify local patterns. Local patterns, it means that for each node, for each variable, we identified in some sense its neighborhoods. We try to identify local patterns around each node. Okay? And since we have the neighborhood of each node, we try on locally to discover a causal structure. And thereafter, we try to merge all the information gathered in phase one and two. And it is what we call divide and conquer. Divide, it means that we discover the causal structure around each node, and thereafter we conquer, that is, we try to merge everyone and to have the global causal structure. Okay, so just to give you some insights, the main point is that we succeed in tackling the large scale setting. So the benefit of the method is huge when the number of variables is large. Okay. And it is in terms, so we tried this on 2 synthetic data sets, and the idea is to see that there is some benefit when you have, for example, 1,000 variables. Okay, and there is also a benefit in terms of times, because when you perform causal discovery, one first feature is that this causal discovery process is very time consuming. And when we do that, we see that we can save a lot of time. We are linear in time. We are linear with respect to the number of variables, and it is the main benefit of the method. Okay, so here it is the causal discovery part. It is the first challenge of causality. Can we discover some graph at large scale? How can we do that in a robust way? So it is the first research direction that we are tackling. Okay, the second direction that we are tackling, it is more about causal inference. It is, are we able to estimate the effect of an intervention? So first I will recall why it is a difficult question, and thereafter I will introduce you about a new research direction that we are investigating, which is considering cluster variables, and it is the setting of cluster DAG. Okay. So just to recall you, so do you have any question about the causal discovery part? Okay. So I will speak now about the causal inference part. So we want to identify the effect of an intervention. So we want to compare the effect of 2 different interventions. Okay, so we have Y, which is an outcome, we have some covariates, and we have a treatment, and we want to compare 2 possible treatments. Okay, and it is what is called the identifiability problem, because in fact it is just that you mentioned at the very beginning, okay, of the seminar. It is a point that all the interventions are not physically possible, and we have to do everything by simulation. So in fact, we have a problem that in fact, intervention, we have no interventional data. That is, we cannot perform all possible intervention. So for example, if we want to know the effect of smoking on the, I don't know, maybe the heart rate variability, we cannot intervene and ask people to smoke. There are some interventions that are not feasible and that are not ethical. So it is the main problem of causal inference. It is that in a lot of time we have only results of experiments, and we have no access to interventional data, and it is our main problem. So what we have to do, we have to be able to calculate this quantity without having access to interventional data. And the point is that we want to replace these quantities with observational ones. That is, we want to replace these quantities, which are interventional quantities. We want to replace this with conditional expectation or output of a regression. We want to replace this with something that you can compute, basically. And it is what we call the identification problem. And the point is that we are not able to intervene, but we have at our disposal the causal graph. So we can do it because we have some additional knowledge, which is the causal modeling and the knowledge of the graph. Okay, so I will just show you what could be a way to identify causal effect, and thereafter I will jump to cluster tag. Okay. So just to show you, I will
just Marianne, for your information, we still have maybe 15 minutes, something like that. So
okay,
if
perfect. So in 15 minutes, I will do it. So I will just explain you two basic situations, okay, which are these two basic situations. So here, what you have, it is you are in what is called a random control trial. That is when you assign the treatment. When you do a treatment, it is completely independent of covariates. And here what happens is that when you assign your treatments, it depends on your covariates. So imagine that you have a medical treatment and that it depends on covariates, for example, on comorbidities, on the weight of the person, on the age, and so on and so forth. Okay, so you have two basic situations. And in fact, here is if everything is independent, if the treatment is independent of the covariates, the situation is very easy, because in this case, intervention and conditioning is the same. And here, if it is not the same, you have to perform what is you have to use what is called the backdoor formula. Okay. So just to tell you, okay. So just to tell you what happens, okay. In all generality, okay. If we are in the second situation, what we have it is that, in fact, if we are in this situation, what we can do, okay, to remove the dependency with respect to x, it is to condition with respect to x. So if we do this, in fact, we are able to conditioning each time with respect to x, we are able, in fact, to calculate the effect of an intervention. So the point is that under some assumption, under having in mind the knowledge of the graph, we are able, using some computational trick, in fact, to transform an interventional formula into an observational formula that is to use conditioning. So what I want to emphasize, it is that in this case, here, this quantity can be, if you compute, for example, expectation of this interventional distribution, if you do this, here you have just to perform a regression. Okay, so in fact, it is something that is completely feasible from the computational point of view. Okay, so I want just to give some insight about what are cluster DAG. So what it is another research of direction. So here, what I show you, it is the case of classical graphs. Okay, so here, just to recall you what happens, we have some variables. Here we have assumed that it is the variables, and you want to estimate the effect of one treatment on an output. And here we are extending this question, considering that X is a group of variables, T could be also a group of variables, and then we may have also a group of variables. And the claim is that the situation where we have instead of variable, group of variables is something very common. Okay, so just to show you, for example, we have, we want to see, for example, we want to study the Alzheimer's disease. Okay, and what you have when you study any situation, most of the time you want to group variables because you have, for example, socio-economic variable, you may have a medical variable, you may have a lot of variables that you want to group. So just to show you also the motivation, in this example, you have also group of variables. Group of variables here, you see in this industrial example, you have variable related to a turbine, you have variable related to heat exchanger, you may have variable related to pressure, you may have variable related to, I don't know, to the subcooler, to the temperature, and so on and so forth. So it is just to tell you that there are a lot of situations when you have a group of variables and when you want to calculate, to compute the effect of an intervention, not only on a variable, but on a group of variables. Okay, so it is here, I summarized here, the situation here. So here, there is, in fact, when you are considering a graph, you may have a group of variables. So here you have two variables that are here, this group. You have four variables, this group. And here you have two kinds of graph. Graph between the groups and graph at what we call the micro level. And the micro level, it is when we try to go inside each group. Okay, here we have intergroup graph, and here we are considering also intragroup situation, intragroup dependencies. Okay, and I will just want to advertise so the recent result of our PhD students. Okay, so in fact, what Clément Ivernès has proven, he has proven that we can perform causal intervention on this kind of graph at the macro level. So what we can do, we can perform intervention on group of variables and see the effect on other group of variables. And that's and the idea is that you may think also that this group of variables that you have here, it could be also embeddings. Okay, so you may imagine that here your group of variables is maybe, for example, an NLP embedding, and you may want to intervene on this NLP embedding. And the theoretical point of view, it is exactly the same that intervening on a single variable, and that's a very, very strong result. So it is a reason why we are very, very interested in what we call the cluster DAG, which is the idea of intervening on embeddings, on intervening of group of variables. So we can do a lot of things. Okay, and we are actually currently working on reducing the complexity of do calculus also. And it is a paper that is currently submitted. So I just want to finish with a last question very quickly, which is a question of the robustness. So first, I want to emphasize this idea that causal models are generative models. So when I show you the structural causal model, it means that we are able to generate data using structural causal model. So it is a very nice idea that has promoted Audrey Poinçon, that is now at Equimetrics. So it is a very nice idea, and we have built of this very nice idea considering causal generative model and investigating in the thesis of Manal the robustness of causal generative models. And if we want to have here we have complex data, we have latent representations that may be causal. And the point is that if we perform intervention, in fact, the robustness of such intervention depends on if the node you intervene on is a source node or a sink node. Okay. So I will finish. So just to summarize, so we have a group. Everything is on our website. So we are organizing several events. Our next event will be in 1 month in Paris. It will be an event where the UQ community will meet the causality community. So you are very welcome if you want to discover our project on our events. And just to summarize some recent papers that we have wrote. So it is about several research directions. So one research direction is about causal discovery. One research direction is about causal inference, considering group of variables. And we are investigating also robustness of causal representation. And we'll be very glad to answer your questions. Thank you very much.
Thank you very much, Marianne, for this very nice talk with a lot of interesting subjects. I think we got already interesting questions, but yeah, please, any question in the audience?
I was wondering about this cluster DAG approach, if you could talk briefly about what kind of clustering schemes are permissible. Can you cluster in any way you want, or do you need to follow certain rules?
There are two possible approaches. The first approach is expert clustering. So, for example, when you have socio-demographic, for example, variables, you have experts that provide you the clustering. A second approach, it is the approach developed by Adèle Ribeiro in a recent paper in 2025, and she developed with her collaborators an approach allowing causal discovery of cluster DAG. And the point is that, as you may imagine, when you group variables, there are also the question of the level of granularity where you gather your variables. And I have no general answer for that. It depends on the application, but it is a very important question. And what I want also to emphasize, it is that there is also this very nice framework of David Blay about hierarchical modeling. And in fact, the question we are wondering is that can we have somehow multi-resolution cluster DAG? And I think maybe it is something that is important to investigate.
All right, thank you.
There is a question from Surya. Please go ahead.
Yes, hello.
Hello.
This is Professor Surya. I am from Istanbul. I'm professor of mathematics, actually applied mathematics. With my research group, we have been working on counterfactuals. I'm curious about in robustness, which metric you use to measure the robustness of the counterfactuals?
Alors, in fact, I can detail this. In fact, in fact, there is this there is a popular metric, in fact, to measure robustness, which is this one, which is a Fréchet inception distance. In fact, what we are doing just to summarize, yes, I will share my screen. Okay. Okay, sorry for that. Okay. Okay. So what we are doing, in fact, we are performing intervention. Okay. And we see the output of our intervention. And what we try to see is how realistic are the images that we are generating. So in fact, the metrics that we are using, it is a metric of how realistic are the image that we generate. It is not a metric related to counterfactual analysis. It is more a metric relative to generative model. So maybe it is because we focus on a very specific problem, but I fully agree with you that maybe we need some metrics for counterfactuals. But the idea, for example, when we generate counterfactual example, when we generate counterfactual images, in fact, we are in the setting of a generative model, so we are biased by the application.
Okay, thank you.
Thank you. Other questions? We see your screen, Marianne. I don't know if you want to share something. Yeah, maybe a question about the applications. You mentioned some of them. From what I know, you are mainly on the healthcare side, but for industry, do you see any specific topics? I think you got an interesting discussion with Christophe related to mainly aeronautics, but
yes, there has been a discussion, and I have just a chat with Catherine. I guess
yeah,
no, it looks like
very nice question with in the chat. Yeah, please.
Yeah, so there are definitely relations with current planning problems we are addressing in the community. And I think about, for example, Robert Goldman, who is doing plan recognition or intent inference. So it means that you try to reconstruct the plans based on the causality, based on a given data set, for example. There are multiple applications of that. And also, you may have also the work done by Christian Muis in Ontario, was working in Watson in the past, who is doing some kind of planning-based ontologies that embed the causalities, and so that you can infer on your data set based on those ontologies. And by inference, I mean logical or maybe Bayesian or Markovian inference, indeed. So those are just some type of examples. But even us, we have been working on these topics, but it's a more complex planning class of applications because it's a polynomial planning class of applications where you can have polynomial algorithms. But it's different type of problem.
Okay, we'd be very glad to
you can
discuss
sometime, if you have strong assumptions, you can have polynomial inference.
Okay.
That's something we discovered recently. We've published that to Ishkai 2 years ago.
What I'm just seeing what is doing Robert Goldman. It's very interesting, and I wonder if there is for example, there are some interaction between control theory, reinforcement learning. There are deep interaction. Yeah, definitely.
That's right. And we work on this also for the control of complex problem, model predictive control, and where there are uncertainties in the models. We work on this as well, on what we call, a user interaction and user intent. In fact, we try to recognize the intent of the user, for example, for controlling an aircraft or a UAV or a helicopter. With Sylvie Thibault in ANU, we also worked on helicopter models, and we have POMDP algorithms with polynomial solvers again. So that could be of interest because when you do massive computations, if you have a lot of data, it's interesting to have near polynomial performances.
And I wonder if there were a challenge. There was a challenge some years ago, a NeurIP challenge for gathering approaches, causality and reinforcement learning. And I think the interaction is very fruitful, and it is really. I think I would be very glad, for example, to set a challenge or hackathon in this direction, because I think there is a really fruitful interaction that are possible. Yeah,
that's a good idea. We could also propose a workshop at ICAPS on this, or AMAS.
Yeah,
I think that could be of interest. That could be of interest for next year, for example.
Yeah, I would be very glad to discuss this with you,
Okay,
because
so
I'm convinced.
Let's keep in touch and discuss about that later. Where are you based, by the way?
I am based in Nancy, but I'm quite often in Paris, in fact.
I see. In Nancy, I work with François Charpillet. Maybe you know him.
He's
well known in the QMDP or MDP domain.
Thank you very much.
I'm working also with the colleagues of Saclay. Also, I'm working with Michel Sebag and Joanne Cohen.
Okay, I see. Michel Sebag, yes, of course. Very interesting. Yes, it could be interesting to meet up. Definitely.
Yeah, with pleasure.
Good idea. Any other question? Maybe I can take a last one, a little one, if I understand well. So about identifiability. So if I understand well, that means if you can infer two causality graphs for which you have the same distribution, the same probability density function. Is that like in traditional clustering or completely different? How do you qualify the identifiability in this context, actually?
In the case of cluster DAG or in general?
No.
In the case of cluster DAG, in fact, yes, there is this question of inferring the probability distribution, the PDF, in fact, basically, because you are using Bayesian network. So you have this question of inferring probabilities. So it is something that there is two steps. There is the first step, which is estimate the structure under some assumption, and thereafter there is also an additional estimation step, which is from the structure to estimate identification formulas, and thereafter it is a statistical step. And the point is that you have several possible identification formula, and you have at some point to choose the best one. And it is actually the work of Clément, who is working hard, but.
Okay, so I suppose this maybe in practice can mean that you can find two configurations of different causality factors that are different from both factors, but the distribution is the same.
Yeah, exactly. And it is very tricky because you have to choose the best one. In fact, you have different things to do. You have to explore the set of all possible formula and to choose the best one from the statistical point of view. And we have worked on the first part, but the second one is tricky, but I think it is crucial for applications also.
Excellent. Thank you very much, Marianne. Any final question from the audience? Don't say hands raised up. So thank you again, Marianne.
Thank you very much for the invitation. And
thanks to all for attending. And
thank you for the nice question. I would be very glad, and feel free to contact me, and we'll be very glad. Thank you very much.